In this example problem, we're going to calculate the concrete shear resistance and the required shear reinforcement for the given section using the AASHTO LRFD general procedure. So you can see it's a single T section with a cast-in-place composite topping. And we have our original untopped gross section properties for our precast section and our composite section properties for our top section. We also have some materials and other section properties shown here on the left. We're using lightweight concrete, and we're given that our lambda for this problem is 0.85. So this is sand lightweight concrete, so we're going to use a lambda 0.85 for it. Our precast concrete has a compressive strength of 5 KSI and our topping concrete 4 KSI. And we have 12 half-inch diameter strands with a 270 KSI strength. Our effective pre-stress is 150 KSI after all losses, and our span length is 60 feet. We have our dead load, which includes the topping, and our live load in kips per foot shown here. I also show us our factored load, which for AASHTO, there are a number of different load cases that we need to check. I'm showing us a strength 1 load case where we take 1.25 times our dead load and 1.75 times our live load to give us a factored load of 2.4 kips per foot. We also have harped strands in our section with a single harping point at midspan. So we have our end depth of our strands and our midspan depth of our strands shown here. And we can figure out our depth of our strands at any section, and specifically the section of interest, which for us is 24 inches from the center of our support. And we can find that just by assuming a linear profile. So assuming that linear profile, we can calculate our strand depth here at the section of interest to be 24.7 inches. And I guess I want to clarify that this is the non-composite strand depth. So if we want to find the overall strand depth, we need to add in our composite topping. As I had mentioned, the actual strand depth for our composite section that we'll use in the shear design is that D that we found on the previous slide plus the thickness of our deck, or our composite topping. So that'll give us an overall depth of 27.2. For AASHTO, we need a couple values that we would get from our flexural design. So I'm just going to give those to us at our section of interest. So our nominal flexural strength I'm giving us as 6,730 kip inches at our section 24 inches from the bearing, or 24 inches from our left support. Then we have our strand stress at ultimate, assuming that our strands are fully developed, would be 265.2 KSI. And considering the development of the strands at this point, we would only have 140 KSI. So we're going to calculate that on the next slide, but I'm just kind of giving that to us here. And then our effective stress after all losses is 150 KSI, assuming we can fully develop our strands. All right, so our effective shear depth here, D sub V, is taken as the distance between our tensile and compressive forces. So our compression force, our tension force, and our dV is the distance between those two forces. But AASHTO tells us that it need not be taken to be less than the greater of 0.9 dE or 0.72 H. So that means that our dV is going to be the max of our MN divided by ASFY plus APS-FPS, which for us is going to be 6,730 kip inches divided by 1.836 inches squared times 140 KSI, which will give us 26.2 inches. 0.9 times DE, which for us, our DE is the distance from the top to the centroid of all of our strands here, or all of our tension reinforcement. So for us, we only have pre-stressing, so this is going to just equal the D that we found above, 27.2, which will give us a value here of 24.5 inches. And then 0.72 times our overall height, which our composite height is 38.5 inches, which will give us a value of 27.7 inches. So we can see here 27.7 is the max, so our DV here is 27.7 inches. So this will be the DV that we use for both our concrete and our shear design and analysis. We're now ready to find our nominal shear strength using our AASHTO LRFD expressions. So we'll need to find Vn as the minimum of these two equations, where Vn is either equal to Vc plus Vs plus Vp, or 0.25 F prime C BV dV plus V sub P. So this second equation here ensures that we don't have crushing of our concrete that controls the shear strength. So the crushing of the concrete in our truss model can happen at the support, and if this crushing happens, then it doesn't matter if we add more steel, we'll still have failure at this limit. So we can calculate our VC, our VS, and our VP components. We'll only have a VP component if we have harped strands, which we do in this case. So to find our VP component, we'll need to find the angle, or our strand angle. So we can do this by taking the inverse tangent of our midspan strand depth minus our end strand depth divided by our total harping length, which for us is half of the span length, so 30 feet times 12 inches per foot, which will give us an angle here of 1.43 degrees. Next, we're going to kind of sidetrack real quick, and we need to check the available development length at this point and compare it to the required development length. So our required development length, we can use the AASHTO code expression, is equal to this value shown here, or this equation shown here, where this kappa is dependent on essentially our member depth. So we have a member depth here of greater than 24 inches, so our kappa is going to be 1.6 times our FPS, which for us will be 256.2. Minus our FPE, which are 2/3 times our FPE, which is 150 KSI, and then times our strand diameter, which is 1/2 inch. So we'll get a development length here of 132.2 inches. Our transfer length we can find from our figure, or from the figure in AASHTO, and we'll get a transfer length of 60 times our bar diameter, or times our strand diameter, 1/2 inch, which will be 30 inches. Our available transfer length is our 24 inches, the distance from the center of our bearing to the point of interest for us, plus half of the bearing because our beam goes to the end of the bearing. So we have an 8-inch bearing, so we're dividing that by 2, and this will give us a value of 28 inches of available development length. So we can see our available development length is less than our transfer length and less than our required development length. So we're going to have a stress in our strands less than this this 150. So we'll need to calculate that on the next slide. Because we're inside the transfer length, we'll use the AASHTO expression shown here to calculate our actual strand stress. So for us, we'll have an effective pre-stress of 150 KSI. This is after all losses, and an LPX, an available transfer length of 28 inches, divided by 60 times 0.5, which will give us a value here of 140 KSI. We can then find our force in the strand at this point, just our total area, 1.84 square inches times this 140 KSI, which will give us a force of 257.6 kips. And then we can find the vertical component of our pre-stressing, just from our geometry shown on the last slide. So 257.6 kips times the sine of 1.43 degrees will give us a VP here of 6.4 kips. So this will be what we use moving forward for our V sub P component at the location of interest. If we did have an available transfer development length greater than our transfer length and less than our development length, we would use this AASHTO equation shown here. So you can see we'll have a linear relationship between available development length available transfer length and transfer length up until we reach our transfer length, and then after that we'll have a different linear expression. So anyway, this is for that next zone here, for this next line. So that's how we find our development length, our transfer length, and our actual strand stress based on our available transfer development length. The next step is to calculate the longitudinal tensile strain in the section at the centroid of the tensile reinforcement. We can use that using the given AASHTO equations. We have a different equation if we have tension at this section versus if we have compression at this section. So you can see if we have compression, we have an additional term down here in our denominator. So we're going to assume that we have compression at this point, and then we're going to go back and check the assumption after we calculate the actual strain. The first thing that we need to do to, complete this equation here, be able to plug in our values, is we need to calculate our different shear and moments at this section of interest. So you can see we have an ultimate shear demand at this section of 67.2 kips, and we have an ultimate moment demand of 1,670 kip inches. AASHTO does have a minimum value for MU, which is the absolute value of VU minus VP times DV. We can see here that the lower limit is less than our actual value, so we'll use our actual MU moving forward. Two other parameters that we'll need are our ACT, which is the area of the concrete on the flexural tension side of the member, and this F sub P naught, which accounts for the locked-in strain differential between our pre-stressing and our concrete. Our ACT, we need to look at the total area below a line drawn in our cross-section at H over 2. So here in our single T section, we're drawing a line and looking at what the area is below that line. So I'm going to assume that's about 2/5 of our gross area. Again, if you have your section drawn up in a computer drafting software, it's pretty easy. You can calculate this area exactly. Here we're just going to approximate the area. So 2/5 of our area, 570, will give us an area here of 228 square inches. The locked-in strain differential parameter, AASHTO tells us that 0.7 times F sub PU is usually appropriate for both pre-tension and post-tension members. So we're going to go ahead and use that value here since we don't have any other information. So we'll have an FP0 of 189 KSI. So at this point, we can plug all of our values in and calculate our strain. So our strain is going to be equal to the absolute value of our moment, 1,670 kip inches, divided by our dV, which is 27.7 inches, plus 0, we don't have any applied axial load here, plus the absolute value of our V sub U, 67.2, minus our V sub P, 6.4 kips, minus our APS, which is 1.836 square inches times our 189. And then all this divided by 28,500 KSI, the stiffness of our pre-stressing times the area of our pre-stressing, 1.836 square inches, plus our ACT, 228 square inches, times the stiffness of our concrete, 4,031 KSI. So we're going to get a strain here then of negative 0.233 times 10 to the negative third. And you can see that this is greater than our lower limit of 0.4 times 10 to the negative third, so this is the value that we're going to use moving forward to find our theta and our beta. Next, we're going to need to calculate our crack angle, our theta, and our beta factor, which is a factor that indicates the ability of our diagonally cracked concrete to transmit shear. So first our theta. Using our code expression, we have 29 plus 3,500 times this, the tensile strain at the location of our pre-stressing strands, and we'll get a theta equal to 28.2 degrees. To find our beta, we're either going to need to assume that we have minimum transverse steel or we don't have minimum transverse steel. We're going to assume that we have minimum transverse steel, and then we're going to go back and detail our section so we do indeed have minimum transverse steel. So to calculate this factor, we'll have 4.8 divided by 1 plus 750 times our strain, negative 0.233 times 10 to the negative third. And we'll get a beta factor here of 5.82. We can then find our VC is equal to 0.0316 times our beta, 5.82, times our lambda, our lightweight concrete factor, 0.85, which was given, times the square root of 5 KSI, times BV, 8 inches, times DV, 27.7 inches. And this will give us a VC of 77.5 kips. So we have our VC, and we can add in our VP, and we can see our total factored shear resistance so far, not counting in any steel shear reinforcement. So for AASHTO, our resistance factor is 0.9 for shear for members with bonded strands. So here we have pre-tension bonded strands, so we can use a factor of 0.9. And we can see that we have a ultimate demand of 67.2 kips, and we have a resistance from our concrete and our pre-stressing of 75.5 kips. So we need minimum reinforcement, minimum transverse reinforcement, but we don't need any shear reinforcement for shear strength. So we only need the minimum shear reinforcement, which we'll calculate on the next slide. On this slide, we're going to find our minimum shear reinforcement, our maximum spacing, and then we're going to detail a bar size and bar spacing to satisfy these requirements. So first, our minimum shear reinforcement is prescribed using the equation that I'm highlighting here from AASHTO. So plugging in our different values, we have a lambda of 0.85, a concrete strength of 5 KSI. We know our web width is 8 inches and our transverse reinforcement has a yield strength of 60 KSI. We don't know our spacing, so we can solve this AV in terms of S. We can then take this times 12 inches to get our minimum shear reinforcement per foot. So our minimum shear reinforcement per foot is 0.096 inches squared per foot. So next we can calculate our maximum spacing requirements. The maximum spacing requirements are dependent on the shear stress in the section, at the section that we're interested in. So our ultimate shear stress is equal to the equation shown here, just our ultimate shear force minus our pre-stressing shear contribution divided by phi for shear, which is 0.9, BV, which is our web width, which is 8 inches, and then our DV, which we found earlier to be 27.7. So here we can see that our ultimate shear stress at this location is 0.3 KSI. We can compare this to our limit, which is 0.62 KSI, and see that we're going to be in this first category here. So our maximum spacing then is 0.8 times DV, or 22.2 inches, and this is less than or equal to 24 inches. So we know that our spacing here, our spacing limit is 22.2 inches. So I'm going to try and just recommend using number 3 bars spaced at 18 inches on center. So we can calculate the shear reinforcement provided by this area of reinforcement and the spacing using this equation here. So our AV is equal to 2 times our bar size. We're going to assume that we have 2 legs of stirrups in our section, divided by our spacing, times 12 inches divided by 1 foot. And we'll get our spacing, our shear reinforcement provided per foot. And we can see that this is greater than our AV required from our AV min expression. So we're okay there. And we can see that our 18 inches is less than our 22.2 inches, so our spacing meets the maximum spacing requirement. So here we can see that number 3 bars spaced at 18 inches on center meet our minimum area and maximum spacing requirements per AASHTO. We can finally calculate the actual shear strength provided by our shear reinforcement and by our section as a whole at this section of interest. So you can see that we're going to assume that our reinforcement is orthogonal or at a 90-degree angle, so vertically oriented. So we can use this equation from the commentary in AASHTO. So plugging in our values, we're assuming that we have 2 legs of reinforcement, 60 KSI. Our DV we found to be 27.7, and our angle we found to be 28.2 degrees. Divide that by our spacing, 18 inches, to get our VS of 37.9. We can add this to our VC and V sub P components to get our total nominal shear resistance of 121.8 kips. We need to compare this value to the limit equation to prevent crushing of the concrete over our support. And we can see the limit here is 283.4 kips, so we're less than that, so this is the value that we'll use. So to find the factored capacity, we need to use our resistance factor 0.9, and we'll see that our phi VN at this point, 109.6, is greater than our V sub U of 67.2 kips. So at this point, we have sufficient strength. We need to check along the entire length to make sure that we have sufficient shear strength along the entire length of our beam, which we'll do on the next slide. We also need to check this longitudinal reinforcement requirement. So AASHTO has a requirement that essentially prevents a shear failure that's induced by a development failure of our pre-stressing strands. So here from our free body diagram, we can see that this tension force in our pre-stressing strands kind of is one of the components that holds together our shear crack. If that steel here that's contributing to that tension force pulls out, then you'd have a shear failure that would occur immediately. So we need to make sure that that tension force, which is all these components on the left side, is greater than all the forces that are kind of wanting that crack to open, which are all on the right side. So here we have APS times FPS, and note that this is our FPX that we found earlier. Needs to be greater than or equal to everything here on the right side. So just plugging in all of our values from earlier, we'll see that the left side 257 kips is greater than the right side 152.3 kips. So our section here meets our longitudinal reinforcement requirement. The shear strength provided from the concrete and the nominal shear strength along the length of the beam are shown here in this plot, alongside the shear demand V sub U. So you can see our phi VC, our phi VN, and our phi VU. You can see along the entire length, our phi VN is greater than our VU, so we know we have sufficient design. One note, our graph kind of has a funny little jump here at about 11 or 10 or 11 feet away from our end. And this is mainly because at this point we have a change in our shear depth. So on the right or on the left side in this region 1, our shear depth is controlled by the maximum of these two. So it's equal to 27.2. Where on the right side, our harp strands kind of fall below this and lead to our dV being equal to the actual distance between our compression and tensile forces. We also have the strand stress changing at this point. So to the left in this region 1, our strand stress is either controlled by having an available transfer/development length less than our actual transfer length or less than our development length. To the right, our strand stress can be fully developed, so it'll be controlled by our flexure equation. So that's kind of the main difference, or why there's that little jump there. But all in all, our design is now complete for shear using AASHTO LRFD.